Hello, everybody. Welcome to this webinar. My name is Raj Ipili, and I'm in the Simcenter test support team. Now, Scott, you want to say something?
Sure, yeah. My name is Scott Beebe. I'm an application engineer with Siemens, working with Simcenter Testlab. Today, Raj and I are going to talk about sound power and how that's done. Fortunately, we're both here and we can kind of help each other out and hopefully give you guys good insight on what sound power is and what it's used for. So Raj and I put these slides together. We're going to go over them together. I think the way that we rehearsed, I'm going to take the lead here on this first part. But our agenda today is to look at some fundamentals of acoustics. What is the difference between sound power and sound pressure? We'll talk about sound intensity and how that relates to the two as well. We'll look at some ISO standards. Usually when we talk about sound power, it refers to a ISO procedure or a procedure that is shared across industry and products, so that when those products are compared in the marketplace, it's kind of an apples to apples comparison as opposed to a number based on a internal test procedure. And then we'll look at how sound power is measured and calculated using Testlab. There's two ways that we can do this. One based on sound intensity. Again, we'll go through how that's done. And then pressure based. So we'll talk about those two things, and then we'll wrap up with questions or comments following the presentation. So sound pressure versus sound power. If we kind of compare the two and we look at these two graphics, we can say that we have a vacuum cleaner, let's say, in the upper left picture there. We have a vacuum cleaner making noise. And if we took a single point microphone with a sound pressure meter and we measured the sound pressure throughout that room, we would get different measurements. And those sound pressure readings would actually be higher the closer we got to the vacuum cleaner and lower the further we got from it. And if we compare that to the picture on the right-hand side of a thermostat or a heat source in the same room, we could measure, similar to the microphone, we could use a thermometer and measure different temperatures throughout the room. And again, the closer we got to the heat source, the higher the temperature reading would be. So if I took that thermometer and I put it right on the heater, it'd be really high. Whereas if I went to the furthest adjacent wall, it would be much lower. Okay. So sound pressure, if you look at the definition up there, is a result based on where we measure it. It depends on the distance. Okay. Same thing with temperature. It depends on the distance from the source that we're trying to measure. So what sound power does is it measures sound and gives you a number for the level of sound, independent of the environment and independent of the location and independent of the distance. So how do we do that? So the next slide starts to get into that. There's two different ways to measure this sound power that we're referring to. There's pressure-based, which is an array of microphones. So where those red dots are there in this kind of half sphere, that would be what we call an array of microphones that would get multiple sound pressure readings. And then based on the ISO procedure there, so for instance, we're referencing a 3700 ISO procedure, we could set these microphones up in a certain configuration based on that procedure. And then we place our object in that microphone array and we run it at a given condition based on that ISO procedure again. And we would get a quick measurement that we could put into the software to calculate a sound power number. And just like it's listed there, that would be a very fast, very easy way of calculating the sound power. And the label that we're displaying there is something that you may have seen when you're going to buy a vacuum cleaner or a dishwasher or a household appliance. A lot of times these labels will be on those appliances, even at Best Buy, just to give you an idea of how quiet or how loud a given appliance will be. And what's nice about this is it's an apples to apples comparison. So when you look at a dishwasher and you see this LWA label, which stands for level watts, okay, sound power is based on a unit of watts, but that's a level in watts, and it gives you 104 dB, you can compare that to another label of the same product that would essentially be done at the same procedure. And you can, again, see apples to apples what would be more quiet or more loud. Now, what's nice about the pressure-based method, again, is it's very fast. But if you are on the development side and this is your product and you'd like to make it more quiet, it doesn't necessarily give you the insight that you are looking for in terms of where that noise is coming from. So we have another method that we can use to calculate sound power, and that's based on a sound intensity probe. So a sound intensity probe, that's kind of a rough picture of it there, but it is 2 microphones that are phase matched, and they calculate a sound intensity with magnitude and direction that allows us to measure sound. And what we would do there is we can put a kind of a grid across the test article, just kind of like what Raj is circling here. And we can take a measurement in each of those boxes and assign an intensity level to each of those boxes and create kind of that intensity map that's shown with the color. And the more squares I make, or the finer grid I have on that test article, the more insight I get. So just based on that description, you can see that that can get really complex, really time consuming really fast, because I can make it really, really fine grid. And for each of those locations, I got to take an intensity measurement, and then I've got to kind of put this into color and overlay it and look into it. So it can be very complex, very time consuming, but the great byproduct of that is I get a lot of engineering insight into where the acoustic hotspots are occurring on my test article. And then we can also use that intensity-based measurement to calculate sound power. And we'll talk about that a little bit too. Okay, so this is the pressure-based sound power. Again, this is the array of microphones. And you can see underneath the graphic there an actual test that's happening in a anechoic chamber where they're testing an article. I believe actually it's a cell phone. They've got their array of microphones around it to find out the sound power of a ring, a dialing ring or whatever it may be. Okay, so we take a number of microphones, we put it over a dedicated area. Okay, typically it's hemispherical like we're showing here. And then we use this equation that we'll talk about here to calculate the sound power. And again, you can see it's on the left hand of the equal sign, it's a level in watts. So the first part, that 10 log, 1 over n summation I to n, that's the number of microphones. So our capital N is the number of microphones that we're going to use. And you can see it's 10 raised to a power, and the variable there is LPI. That's the sound pressure level measured with each microphone. And then we add all those up for the number of microphones we're going to have. Okay, so that gives us our first measurement for this equation. Then if you notice, there's actually 2 constants. All right, there's a K1 and K2. So K1 listed here is the correction for the background noise. When I'm doing the array method, I typically am going to use a noise room. And the reason for that is I want to be at least 6 decibels above background noise. So I want whatever I'm testing to be the loudest noise source that's being measured. And when I'm in an anechoic chamber, that's more easily obtainable because I'm most certainly going to be above the background noise by 6 dB. The recommendation is to be 15 dB above background, and that would absolutely require an anechoic chamber because essentially at that point we're removing any background noise. For K2, that's our correction for the environment. When we turn on our noise source and it has reverberation or kind of echoes in the chamber, we can take that out as well. So that would be, we satisfy K1, we're in an anechoic chamber, but maybe our anechoic chamber doesn't have the absorption we need at specific frequencies and it actually has a little bit of reverberation. We can back that out, and that's the K2. And then finally, that 10 log S over SO is essentially the calculation for area. So S sub O, or S sub 0, I should say, is 1 meter squared. So we plug 1 meter squared in there, and then we calculate our area, and then we take the 10 log of that, and that's the third constant. So it's not just measuring the microphones, we have to account for both the background noise, test environment noise, and then also the area. And those can all be easily calculated using Testlab and the math for the area. But to measure the background noise, to maybe take a step back, essentially we're going to literally measure the noise in our test environment with nothing on. And then again, what we can do for the reverberation is we measure the amount of decay or how long it takes for the noise to dissipate, and then Testlab will calculate that K2. Anything I missed there, Raj?
No, Scott, you covered everything very well. I just want to mention that this first term is that it is the average sound pressure level. So
Yes.
to compute the sound power, you are using the sound pressure level and then taking that area into consideration to compute the sound power and applying the correction factor.
Okay, so sound intensity. So we've covered the pressure method really hard. Let's talk about the intensity method now. So again, sound intensity is a vector quantity. Okay, so it describes the amount of, essentially, without reading the definition, I'll put it this way. Sound intensity is a vector quantity with magnitude and direction. So what I can get from the sound intensity is how intense the sound is and the direction of it. So if we go back to our heater example, if I wanted to know the power of the heater, that would be classified for me in the user manual or somewhere else. But let's say I wanted to buy a heater that was at least 500 BTU. That would be similar to the sound power rating, where I'm looking at my dishwasher and it has a sound power of 104 dBA. The heater would have a measure of BTU, or could even have watts too in terms of the power outputs. But the intensity, where that heat is coming from, the intensity of heat is going to be much higher where the heater blows the heat as opposed to the backside where I plug it in. And the same idea holds true when we talk about sound. So for the dishwasher, the bulk of the sound is going to be coming out of the front door where you load the dishes. The rest of it's enclosed and it has sound absorbing material, but the bulk of the sound is going to be coming from the front of the dishwasher where we load it. And if we were to use an intensity probe, we'd be able to see that. We would see that the intensity of sound would be higher in the front of that dishwasher than the back. And this is the equation for intensity. So we're going to look at the sound pressure and the particle velocity. Okay, essentially, what is the velocity of the particles being moved by that sound pressure? So there's a lot of math here, but what ultimately I'd like you to take from this slide is that we're going to look magnitude and direction of where the sound is coming from as it comes off of that sound source. And that'll provide us the insight. And we can also use that for sound power. So if we look at the box equation that is here on this slide, you can see it is watts per meter squared. This is how we get that sound power. So sound power, like we said, is measured in watts. Well, here I have watts divided by meters squared. So if I multiply by the area I've scanned using that intensity probe, then I get back to watts, which is ultimately what I want for sound power. So sound intensity is watts per meter squared, or power per area. And if I back that area out, then I get back to the sound power.
So as Scott mentioned, sound intensity is a vector. So it has magnitude and direction. Whereas the previous terms which we talked about, the sound pressure and sound power, they are scalar quantities. So they don't have any direction associated with them. That is the great distinction between the intensity and sound pressure. It is a vector. So what that allows us to do, it allows us to do measurement in an areas where there is a lot of background noise measurements, because intensity measurement coupled with the area, it is not affected by the background noise. Here is an example to show that. So suppose you are measuring, say, vacuum cleaner that we had, and it is radiating sound all around. And if you measure the sound intensity along the surface and along the surface area, and if you take the summation of the intensity times the area, you can get the sound power from it, shown by this uppercase P. Now, if you are in a situation where you are measuring when there is the vacuum cleaner is outside and you are measuring in an area, and so this is like the vacuum cleaner is making the background noise. And if you measure over the same area and the vacuum cleaner is not within that measurement, and in this case, still the vacuum cleaner will be radiating the sound, but if you take the vector sum based on the product of the intensity vector and the direction, normal direction vector for the surface area, then the summation over that entire area will give us a sound power, which is actually will be equal to 0, because there is sound coming in and going out, and because it's a vector quantity, it will get summed to 0. Intensity measurements can be performed in situ. So even in a factory floor, for example, where there can be a lot of background noise, you can still perform that. You don't necessarily need an anechoic chamber for doing that type of testing. That is the great advantage with the intensity, is that the background noise has very little influence on it, And so you can do the measurements to compute the sound power for it. So now that we know a little bit about intensity, let's see how do we actually do the measurement for intensity. So intensity is nothing but the sound pressure times the particle velocity. So the particle velocity is the velocity of the point moving at that particular location wherever we are measuring. So it can be measured in two ways, the intensity that is. We can measure it using what is called as a pressure probe, where there are two microphones which are separated by a small spacer in between them. So you can see there are two microphones here on this probe, and then there is a small spacer, this black thing in between. And these are called as phase matched microphones. They form a pair such that there is little phase difference between them, and that is very helpful to capture the intensity. And then there is the other type of probe called the PV probe, the pressure velocity probe. There is a microphone in there, and then there is a particle velocity sensor also in there. And you can directly multiply pressure times particle velocity to compute the intensity. If you consider the case of this PP probe, pressure probe, you have the two microphones which are separated by that fixed distance. You find the pressure difference between the two microphones, and knowing the distance based on the spacer that you used, you can compute the gradient of the pressure from which you can get the particle velocity. So when you do that, the frequency range becomes limited because it will be based on whatever the spacer size is. So if you use different sizes of the spacers, the frequency range will change. Whereas if you are doing a PV probe, you can cover the full range in one single go. So there are pros and cons to both approaches. So in a PP probe, it's more widely accepted, but in a PV probe, it has like a thin platinum wire in it, and that is sometimes prone to damage. And also one other thing is that this PV probe, it has frequency dependent calibration. So its calibration factor is not a constant, but it changes as a function of frequency. So you have to account for that. Either of the techniques can be used for measuring the intensity. There are some ISO standards for doing the sound power using the intensity. The standard is the ISO 9614. There is a first part, which means that the entire surface around the test object can be discretized into smaller points as shown here, and you can measure the intensity at each of these discrete points to compute the intensity, and from that you take the area into account to compute the sound power from that when you sum the whole thing up. And the other method is the measurement by scanning, where instead of discretization, you are doing a scanning of the surface. You take the intensity probe and scan the surface, first horizontally and then vertically. So do it 2 times on each surface, and you can get the intensity for each of the surfaces, from which you can then compute the sound power. The scanning method, as it looks, it is simpler, whereas the discrete point measurement, it takes more time because you need to acquire data at more discrete points. And so it is more time consuming, but with the discrete point measurements, you can get better insight into where exactly the noise is coming from. Not just in terms of which surface, but also which point on there is making the most noise. So you can get that insight. And following this ISO 9614 standards, there are some judgment criterion also established in them to tell us, hey, what size of this grid is needed, how many points of this grid is needed. So they tell us there are some data quality indicators which are governed by this F1 to F4 for the discrete point measure, and there are 2 criterion similarly for scanning. Using either of these 2 techniques, you can compute the sound power from that. As Scott mentioned, sound power represents the total energy coming out from the test object. And the test object can be something like a vacuum cleaner or home appliance or an earth moving equipment or something like that. There are some industry specific standards for these type of measurements. And here there are, so for example, for hand power tools, there is an ISO 15744 standard for that are specific to that, defining how to do the measurements and how many points to do the measurements and such. So there are some general standards also, but there are some industry specific standards also for that. So now we talked about different terms when we talk about sound intensity, sound power. This slide is a summary of what we discussed so far. So as we said, sound power, you can compute it based on sound pressure or sound intensity. When you do the sound pressure method for sound power computation, if there is no influence of the free field and background noise, then no corrections need to be applied. But then if there is a lot of background noise and then the environment is not ideal, then you have to apply this K1 and K2 correction factors. For the sound intensity, you can do the measurements using a PP, pressure probe, or a pressure velocity probe. And each of these probes, you can do the discrete point method and the scanning method. And there are different tools in Testlab to allow these measurements and calculations. So for sound pressure, you have the signature acquisition, and then sound intensity, you can use this sound intensity testing module of Testlab. And for applying these corrections, there is another module for that, the sound pressure based on sound power, that's an add-in in Testlab. And then for the intensity data, you can process that in the intensity analysis module of Testlab. So as you can see, all the different things that are needed for measuring sound power, the capabilities exist within the Simcenter Testlab software. With that, let's take some demonstrations of this capability in Testlab. Scott, you want to start showing that?
Sure. Take the screen from you here.
Okay.
Okay, yeah. Everyone see Testlab? Or I guess Raj is
Yes.
the only one that can tell me whether or not you can see it. Perfect.
Yes, I do see it. Good.
All right, so what we have here is, if I go through the throughput, I have 10 microphone positions that would be in an array over a test article. And we run this according to the ISO procedure, similar to what Raj and I have referred to, and we get our sound pressure measurements. So if I were to do, just to plot these, just so you guys can see them, this would be the raw time data of each of those microphones. And I'm not going to put them all in real, but you guys get the idea. So I have 10 sound pressure measurements that span for about a minute. I'm going to load those in my time data selection. And I can look at those and see what kind of data I have. And then I'm going to jump over here to time data processing. And this is the throughput method that Raj is referring to on the slide previously shown. So I'm going to process all 10 microphones. Under my acquisition parameters, I can set my tracking and triggering, where we ran this for 60 seconds. We're going to do 2 averages per second. And essentially, since we're saying it's stationary, the product that we measured was run at a stationary constant running condition. And so we just want that one measurement. And then under channel processing, I'm going to come, this is where I would be to start, but I'm going to come over here to derived. And this RTO stands for real-time octaves. So when we look at sound power, normally we use octave-based processing because we as humans, we hear more in an octave range as opposed to narrowband. So when we report sound power numbers, we typically use octaves. And the real-time octaves is based on ISO procedures normally. Without getting into too much detail on that, that's what we would use. So there's a couple things we'll want to have turned on to be able to do this. Under tools, add-ins, we'll have the real-time octaves turned on.
ANSI IC octave filtering.
Yeah, that's right. I always look for RTO, but it is under ANSI. So ANS, this one here. So the ANSI-IEC octave filtering turns on those real-time octave standards. The other thing we'll have turned on is sound power based on sound pressure. So those 2 add-ins need to be turned on to be able to do these calculations.
Well,
so again, yeah.
For this derived channel, you don't need the sound power based on sound pressure. Okay.
Oh, okay.
So
I was mistaken in that then. I apologize.
No problem.
Okay, so when those turned on, I would insert a formula, and there is sound power, just like what we were looking for. If I open that up, there's a value, and this value is essentially the constant, the sound power constant. The function is going to be the microphone. So in our case, we had 10, so I would hit this until I had 10 functions to put all the channels in that I want to calculate for my sound power. So we're not going to use this one. We're going to delete this guy. And we're just going to use these 2 that are already made. So if I say edit here, you can see we've got channel 1 through 4 and 9 through 14. Okay, so we're using these channels for our calculation, and our sound power constant This is essentially accounting for our area for our equation. We're also going to look at just the microphone average or the power average, just so we can show you some differences there. Once those are set, I hit calculate, which I've done already, and I'll show you some results. So here is each individual microphone, 10 positions calculated for us, and you can see the different varying calculations, just like the thermometer we referenced before with the heater or the sound pressure level meter that we used with the microphone throughout the room. I'm going to have different readings for each one of my microphones depending on the location of those microphones. Here is the microphone average. You can see the overall here is 78.46. This is still in pressure. And then what we are hoping to get is our sound power, which is 86.46 in watts. Now, the difference, Raj and I, we talked about this just before the presentation here, but the difference here, this 86.46 and this 78.46 has a lot to do with that constant that we added. Okay, notice it's 8. It's a value of 8 higher, so 86.46 and 78.46. So that accounts for that constant and the area of the microphone array that was used for this testing. So that's how we would calculate the sound power based on sound pressure and throughput processing. We would measure all our microphones and then we can put it through those equations. Anything to add there, Raj?
Yes, Scott, I was going to just say that if you don't want to apply any of the correction factors, the K1 and K2, so that will be some measurement like in an anechoic chamber. There is very little influence from background noise and the room is not reverberant. So all the sound radiating from the source, it is absorbed by the walls, right? And it's not reflected back. In such an environment, you don't need to apply the correction factors because the background noise is well below the measured sound pressure level and there is no reverberation. So K1 and K2 can be ignored in that case. And you can directly apply the area correction factor, which is the value of corresponds to 8 dB based on that area that we measure. In a situation where there is background noise and the room is not ideal for doing the measurements, then in that situation, you will have to apply the K1 and K2 correction factor. And to be able to apply that K1 and K2 correction factor, you need this add-in. So for that one, you need the sound power based on sound pressure. That add-in is needed. And this add-in is a tokenable add-in which uses 19 tokens. And it also requires as a prerequisite the ANSI IC octave filtering add-in. So I'm going to say OK. And then we will see different tabs here at the bottom. With this add-in, you get an extra capability. And first, let me do one thing. I will put the same data that Scott showed, and I'll put it similarly in the input basket. And I'm going to see that here. And as we saw, it is like a stationary sound. But when we add this add-in for sound power based on sound pressure method, we will see that there is a tab that gets added in sections, which is called sound power tab. In that tab, this is the graphical user interface where we specify the correction factors and the settings needed for applying these correction factors. Here we specify the measurement area, which is the 6.28 meters square, and 10 times log of this value is that 8 which Scott put in for the calculation of the sound power in the constant there in his formula set. In this case here though, we'll just specify the area directly and you have the option to do the compute the sound power or the background noise. When we are applying the K1, K2 correction factors, so first we have to do a measurement, the object under test, like just by itself. So we'll measure some sound power from that. And then we can measure the background noise with the source turned off. We'll just measure the background noise, and this background noise can be from the airflow in the ducts or noise coming from adjoining test cells or whatever. And that is the background noise. We'll measure that. And then one other thing which has to be measured is the characterization of the room environment, which will be done based on a reference sound source. So first we measure the uncorrected sound power of the object under test, and then we measure the background noise. We can apply the K1 correction factor based on the background noise. For the K1 correction factor, if the background noise is less than 6 dB, if the difference between the background noise and when the source is running is less than 6 dB, then you apply a correction factor of 1.3 dB. But if it is greater than 15 dB, you don't need to apply a correction. And when it is between 6 dB to 15 dB, you apply a formula, and I'll show you how that is done. For the K2 correction factor, you use a reference sound source in the same environment and then do the measurement with that, and you compare that reference sound source, the sound power you measure from that, and compare that with what it was calibrated sound power, and that gives calibrated, that is coming from the manufacturer. They would give you the calibration sheet which has a sound power also. You find the difference between what you measure in the test environment using the reference sound source and compare that with the calibrated sound powers from the manufacturer of that reference sound source. You find the difference and then apply the correction factor based on that. Or there is one more way to apply this correction factor, K2, and that is through a reverberation method. Finally, once you measure the total sound power and then apply these correction factors, then you can get the corrected sound power from that. So let's see how that is done in Testlab. So here we have 3 sets of measurement. One is run 1, which is the object when it is running, like this source. Then we also have the measurement for the background noise. And then we also have a measurement for when the reference sound source is running. So using these 3 data sets, and in addition, actually, we also have the calibration sheet for the reference sound source. That is also included in this project. You need to know that, and then we can use that for applying these correction factors. We already added the data in for when the object is running. Notice that I'm using similar settings that Scott had used. We specify that. And then under section, we will say, hey, we want to measure the sound power. We have put in the area, and I want to measure this sound power over this frequency range. And so we are not applying the K1 and K2 correction factor just yet. And here there are some warning signs to tell you, what should be the typical processing parameters that need to be used. We have already specified that in these acquisition parameters here. So once I have that, then I can measure the uncorrected sound power. Oops. And then I can hit calculate. So these results will be stored as a run in Testlab. Then the next step would be to load in the background noise, and background noise measurements performed with the same microphone positions, and we'll use then the background noise option to compute it. From that, we can apply what that gives is result like this. So first we have this uncorrected sound power. So over this frequency range of 50 Hertz to 10 kilohertz, you can see that the total sound power is like 86.4 dB, and this is sound power. Now, when we do the measurement for the average sound pressure for the background noise, and we find the difference between the sound pressure when the object was running to the sound pressure that we measured as the background, then this level difference curve is computed from the background noise measurement. And this graphic shows that. It shows the difference between the noise from the object under test from the background noise. So at lower frequencies, the difference is about 3 dB at this 63 Hertz. Until we reach this 125 Hertz, the difference is less than 15 dB. So you will see that as the frequency goes higher, the difference between the background noise and the object under test, that source, is greater than 15 dB, and so no correction needs to be applied over this frequency range, going from 125 Hertz and above. Over these lower frequencies, at 63, 80 Hertz and 100 Hertz, there is a correction that needs to be applied. And that correction, when you apply that, this is the result of the comparison between the green curve here is the uncorrected one, and the blue one is by applying the K1 correction. And so you can see that at 50 Hertz, where the background noise was pretty high, you applied the correction factor, and that correction factor is actually 1.3 dB, because the level difference was less than 6 dB, so the correction factor is 1.3 dB. As we go higher in frequency, no correction needed to be applied, and that is why you don't see any difference between the levels of the two curves. Actually, when we take the data and when we do the computation using that add-in for sound power based on sound pressure, in the data properties, it shows whether a correction factor has been applied or not. In the data, you can see first one is no correction has been applied, and the second one is with the K1 correction factor applied. So when you do the computation using this method, the data is annotated such that you can easily refer back to it later. Similarly, we do the same processing with the K2, and then when I do the K2, I compute the sound power from that. You can see that using the watts in dB. So, and we found that this sound power for the reference sound source is shown by this green curve, and blue curve is showing what we measured. As you can see, there is differences between them. At lower frequencies, what we measured was higher, and at higher frequencies, what we measured was lower for that same reference sound source. So this calibrated sound source, that is what we got from the calibration sheet from the vendor. This room environment, it produces some differences, and that is what the environment correction factor K2 is for. What we measure for the sound power is not matching with what exactly we got from the calibration sheet, and so this correction needs to be applied. The K2 correction factor is the difference between what we measured to the reference value from the calibration. So that is about 5 dB at these lower frequencies, and it is actually a negative value at some other frequencies. And then once you apply the K1 and K2 correction factor, then this is how the final result looks like. The pink curve now has the K1 and K2 correction factors included in it. As we saw at lower frequencies, what we measured from the calibrated sound source in that environment was higher than what in this spec sheet. So we need to subtract that from the total sound power. And that is what we get by applying this K2 correction factor. Notice that the total sound power, it made about a 1.2 dB difference in terms of the total sound power. When the environment is not right, the measurement environment, you need to apply these K1 and K2 correction factors to be able to get the correct sound power values. So that is how you do it. Then next, let's take a look at how to do the sound power based on intensity. In this example, what I will show is there is a test object. You can see in the top left-hand side here. We created an imaginary measurement surface using these cubes, and we split that surface area of each side into small grids, and we measured the sound intensity at each of these points within this grid. And finally, we can get a result like this. You can see the sound intensity is higher on this side here, which is the left side, and it is coming from a specific location. And actually, you can superimpose the picture of the text object in the result also, so that you clearly know where exactly the hotspots are. So that is the engineering insight you get from doing the sound intensity method, the discrete point method in sound intensity. So let's see how this is done. So when I go to this window and then I go to this intensity method, this data, we had performed the measurement of the sound intensity on each of those surfaces in each of the points, and they were numbered back surface 1, 2, 3, so on, and front and left and right and top. All of those data points have already been measured. If you use the Testlab sound intensity testing module, measurements can be set up very quickly and done in a very efficient way, moving from one point to the next. I have loaded the data from the intensity measurements, the discrete point intensity method, and there is an option here for doing the processing with the 9614-1, which is for the discrete point method, and the 9614-2, which is the scanning method. So let's see if I can load that data in. Add to the input basket, and so similarly the right side and the top side. So go to the intensity analysis tab. I'm loading the data from this input basket, and when I load it, it will show us this list of the functions which are available based on our measurements. So M here is measured and C means calculated. So we had measured at these points, the front side, left side, right side, top and back, like that. So the intensity and the pressure were measured, and C means calculated, and that is the sound power. So from this discrete point measured for each of the surfaces, you can compute the sound power for each of the surfaces. And you can see you can see the sound power for each of the surfaces. And in addition, based on these measurements, it computes this data quality metrics, this F1 to F4, which in Testlab we have translated it to give like this criterion. So it becomes simpler to check because each criterion we want to make sure that it is greater than 0. These are automatically calculated based on the collected data. And from these, you can use this data to compute the total sound power over the different frequency ranges. So these data quality metrics, they exist for all the surfaces. And for some of them, you can see at lower frequency, it is showing red. So that means intensity is going in rather than coming out. So from these, you can calculate how this intensity as a function of frequency for the different octaves, they are calculated by adding this calculate. If you click on calculate bands, they will be calculated and you can get a results preview here itself. And here I have that surface. You can see that for this frequency range of 63 to 3000 hertz, this left side, that is what was making the most noise, right? If you recall, in our test object, there is a small motor there, so that was making a lot of noise, and it's correctly identifying that. Notice how for the top side here, I have included the picture. Similarly, you can include picture for each of the sides as well. And once you have the results, you can save them and then be able to look at the results. Here I have an example result computed. And if you look at the calculated functions, calculated 2D functions, you will see a lot of different metrics are calculated for each of the data quality metrics for F1 to F4, and the sound intensity for intensity and the sound power for each of the grids and the total surface. So back 1, back 2, those are each of the individual points, but sound power of the back is for the entire area for the back, and similarly front surface, top, etc. From that, you can plot it and see, hey, this is the total sound power and the contribution of each of the individual sides. You can plot that and see that here. Along with these results, you can get the sound power maps also, which you can then plot it here. Right? So you can just drag and drop that into the display. And this is called as a geometry acoustic display. This is one of the tabs here. And what we have created is an acoustic mesh geometry. So this acoustic mesh geometry, this is not like a standard modal testing geometry, but an acoustic mesh geometry. You can make that from here with the geometry add-in called generate acoustic mesh. And you can superimpose the picture for each side also. When you're talking to somebody in the design or something, then it is really very useful to convince them or make them understand where exactly the noise is coming from and such. You can see such a result here. So you can see the left side, it's making a lot of noise, and there is a hot spot right around the point where that part which makes a lot of noise is located. We measured similarly on the other surfaces also, but this left side is the one which is making the most noise. Scott, you want to give a preview of the surprise element?
Yeah, if you go to the presentation, I think I can cover the highlights in just a couple minutes.
Okay, good.
So we talked about the benefits of using an intensity probe to essentially localize the hotspots or the acoustic hotspots of where the noise might be coming from. One tool that we have that uses the principles that Raj and I talked about today, especially when it comes to sound intensity, is known as the Simcenter sound brush. And the Simcenter sound brush is a quick and easy way of doing this intensity testing that Raj just discussed to get these vector quantities and hotspots displayed really quickly. What is used here is, if you look at the wand here, if you look at the wand that is being held, there is a ball that lights up, and that ball is tracked by the camera shown next to the computer. And so we don't have to make the physical grid like we did before in Raj's test results, because that's automatically done electronically. The camera is able to position where that ball is in 3D space and where the measurement is taken in terms of intensity to give you the result that's shown in the software there with the number 3. So I'll get all these intensity vectors, and I can put a cutting plane through those vectors to see the acoustic hotspots as to where those things are. And I can visualize that based on a specific frequency band that I want to look at to determine where the noise is coming from. This is what's included. So again, the light up ball, it tracks in the X and Y based on the position of the ball, and then based on the size of the sphere. Based on the size of sphere, it can tell you where it is in 3D space. So it always knows where it is. And then internal to it, there are electronic gyros to let me know the position that the wand is being held. And that's important on the next slide. If I was to show the accuracy of the tool, we're going to use 4 microphones to calculate the intensity, which allows us to hold this in any orientation as opposed to normal to the surface, like Raj said. So if I'm doing development and I want these type of results quickly, as opposed to the more laborious traditional intensity probe test that we've talked about, I can use this tool very quickly to get some intensity results for the source localization to look at what parts of the test object I want to go after to reduce the noise. That's kind of the sound brush in a nutshell.
Okay, excellent. Scott, you completely stole my thunder. Well, I was showing this great tool for engineering insight, and you come up with this magic wand, so to speak, right?
That's right.
Yeah. So that's a great capability. And like Scott said, like it's not, sound power is not based on the ISO standards, but for engineering development kind of a thing, it's an excellent tool for getting an A to B comparison. Let's come to the last slide here. And so we looked at the Simcenter Testlab capabilities for computing sound power using the pressure-based method and also the intensity-based method. As you can see, we can do it all. Testlab has all this capability. All this capability is available through the Testlab tokens concept of licensing. In the pressure method, we saw that it was quick doing things and we get mostly one sound power number, whereas the intensity method, it takes more time to do, especially with the discrete point method, but it can give you more engineering insight, and that is helpful for troubleshooting, for example, like hotspots. Either way of doing things is okay, but when you have an environment where it is not conducive for doing the pressure measurement, maybe use the intensity-based method. Finally, we want to mention that the Simcenter Test community website has a lot of excellent articles on a wide range of topics. And here I have listed some of them which are relevant to this particular topic, but there are a lot of other topics also. And like Scott mentioned, even for the sound brush, everything you need to know, that is also included here. So thank you very much for the opportunity to present today. Our contact information is listed here. So if you have any questions, please feel free to reach us. We are more than happy to assist in any way with your sound power computation and beyond.